As we start the work on Math 1, or 1127 as it's called, finite math, we'll begin with our first lesson, Chapter 1, Section 1, on linear equations and inequalities. And I just thought I'd mention this, give her a little plug here. Danica McCullers, who is an actress and has also moved into the area of mathematics, has written a number of books, very interesting, mostly for young teenage girls. Some of the past ones dealt with pre-algebra, but this one is called Hot X Algebra Exposed. And it's a very down-to-earth treatment of what for some is a somewhat frightening subject, algebra. And I started to read it, and it's pretty good. So I recommend that if you feel uncomfortable with certain parts of algebra and want a real basic, friendly approach to mastering which some think is a difficult subject. We'll try to treat that too as we go along. And what I'm using, again, for our lessons here is the actual Finite Mathematics textbook, which is available at the front desk. You leave your ID card, they'll let you borrow a book, or if you look online, you do have an e-book there, and you can look at the pages at home and take notes as needed. So what I plan to do is go through the examples that are given in the book with a little personal touch. First of all, what is an equation? Well, an equation is something in which you have a mathematical expression, and between them you have an equal sign. So a mathematical expression made up of terms and algebraic symbols, and an equal sign in the middle. That is what an equation is. Now a linear inequality, instead of having an equal sign between your mathematical expressions, you have an inequality sign. And we will be showing you examples of both of these as we go on. Now, what I've written here over on the side are very, very simplified steps of what you need to know and to follow as you go to solve either an equation or an inequality. One of the first things you want to do is to clear fractions that may be in it. And we see a fraction here and a fraction there. Then you want to remove grouping symbols, whether they are parentheses, these are the most common, or a fractional division bar, which is a grouping symbol. And we see them here in a number of places. So we'll be doing that in our first example. Then another very important thing is you combine like terms. And then you're going to use a technique that you may not know the name of, but it's moving terms from one side of the equation to the other simply by changing their sign, which is called to transpose. Then you want to solve for the x. And there's usually a term with the x, a number, which is the numerical coefficient, and you're either going to divide or multiply by that coefficient. And we'll be illustrating these as we go on. And then another good thing is to check it. Sometimes the checks are more difficult than the solution, but MathLab allows you just to put the answer in and click on check your answer, and it tells you if you're right or not. So let's look at example 1 here. So we see it is an equation because of the equal sign. There are parentheses, but there are no fractions. So the first thing we're going to do is to remove the parentheses by using what we call the distributive principle. And we'll do that to both sides. So this just becomes 8x. A negative 3 times x is a negative 3x. And here's where you need to be careful. A negative 3 times a negative 4. A negative times a negative gives you a positive 12. Here this will be 3x minus 12 plus 6. So our first step was rather easy. All we had to do was to get rid of the grouping symbol. And now we're going to use our third item here, combine like terms. Well, here we have an 8x and a negative 3x that we can actually subtract and get 5x plus 12. And then here, there are no x terms to combine, so this is going to be 3x. Now here we have a negative 12 and a positive 6 that when we add or subtract, depending how you look at it, it's combining terms with different signs. This becomes a negative 6. Now this is where we want to be, somewhere in the solving of this equation. And that is to have a variable and a term, a variable and a term. Now we want to get all the variables on one side, all of the terms on the other side. So what we're going to do is subtract 3x from this and 3x from this. So that leaves us with a 2x on this side. And again, we're using that transposing technique. We take this term to this side, it changes its sign, and it becomes a negative 3x. That gives us a 2x. Now we bring the positive 12 to the other side, or subtract 12, changes the sign. This becomes then a negative 12 on this side. So this will become a negative 18. So a negative 6 and the negative 12 we're subtracting from both sides, or transposing, gives us a negative 18. Now we're ready for step 5, where we have 2x is this, but we only want one x, a positive x. And for this, we look at the numerical coefficient of x, which is 2, and we're going to divide by 2. And we then get x, as these cancel out, is a negative 9. And if we were to put our negative 9 into the original, it would check. Now in your textbook, they do show you the check. Now, a couple of interesting things before we go on. We have written the equation clearly and neatly. We have followed some rules, gotten rid of the grouping symbols. Notice I've kept my equal signs sort of lined up, and my steps are clear as to what we're doing. Now, this series of steps is called, believe it or not, solving an equation. And generally speaking, in a math class, you need to show your work where you have neatly written your example, follow the steps in some sort of order, and then arrived at a solution. These steps are called solving an equation. And it works on the principle that what you have, something on one side is the same. And as you either take away things from one side, you take away from the other, add things to one side, add the same to another. So where it's no longer the same equation, it's an equivalent equation. That's basically what you do. And then eventually you find out what that magical x is. It has some value. That is algebra. Going on to example 2, we do see here now an equation with fractions. So we're going to use step 1, clear fractions. And the rule is you multiply each term. Terms are separated by a negative or positive sign. So this is one term, one term, one term. Multiply each terms by the least common denominator that we have to figure out between a 2 and a 3. And we'll give you a moment to figure that out. And that's 6. So we're going to multiply each term by the common denominator 6. And I put it in red so you could see it. And this is to indicate multiplication. Now, here's the key part. You're now going to take the 6 and cancel it with the 2. Well, 2 goes into 2 once. 2 goes into 6 3 times. 3 goes into 3 once. 3 goes into 6 twice. And here there is no denominator, so you don't do any canceling. Now, every number has a 1 underneath it. When it has that 1, we don't write it. So in a sense, we've gotten rid of the fractions. But now we have a grouping symbol, this division bar. I can put parentheses, because now I have to clear the parentheses by distributing that 3 to each term. So 3 times x gives me 3x. 3 times a positive 2, a positive 6. Now here, again, you have to be very careful about signs, and that's why neatness is important. There's a negative 2 times x, which gives us a negative 2x. And then 6 times 5 is 30. Now another step that never hurts is to go back and check your work. I think we're good here, but you may want to check your signs, or whatever area you're weak in, you may need to spend a little time on that. We've done the first 2 steps. We're now going to do the 3rd step, combine like terms. This just gives us an x and plus 6 equals 30. Now we have group-like terms. We're going to transpose. The only thing we need to transpose is the 6. Another technique is you're going to subtract 6 like this. I see a number of students have used this. This leaves us with an x here, and this leaves us with a 24. X equals 24. And that actually is our solution. Again, we can take this, the positive 6, bring it to the other side. There's where our negative 6 comes in. A sort of a shortcut. So once again, we'll see some of these, and of course you're going to have practice, and then your quiz bees, and eventually your test on this. As we go into example 3, it's solving equations that are actually formulas, but for a certain letter. Now, we still use these same techniques. So let's see what we do. So, by the way, these are formulas you're going to be using in Chapter 3, and you might wonder how we get all those different formulas. Well, we want to solve this equation, this formula for the letter R, and then later we're going to solve the same equation for the letter P. And what techniques are involved? Well, the first thing we need to do is to isolate the term we're looking for, which is R. So R is in this term. We want to get R all by itself. So I'm going to take this P and transpose it to the other side. So I then get A minus P. So all I did is I subtracted a P from there, subtracted a P from there. But this is where this technique of transpose comes in very handily. By moving it to the other side, just change the sign. And you get then P R T. I guess they're out there cutting the log today. Okay, now there's our R. How do we get R out of a series of, in a sense, factors? This is P times R times T. And the answer is, we do so by dividing. We want to get rid of the P, we divide the P. The T, the same. But then we must do it to this side. So P, T. So here the P's cancel out, the T's cancel out, and we're left with R all by itself. That equals this. And that would be the formula for rate. In this one, we have to do something first. And we have a P in 2 places. Now remember, there's a 1 before every number. We're going to need that here in a minute. So this looks like then A. And I'm going to factor now out the P, because I want to isolate that P. So that'll be a P that I'm taking out of each of these 2 terms. And I'm left with a 1 there. There's my 1. To indicate that's where the P used to be, plus RT. So this is equivalent to this. But I've isolated, in a sense, the P. It's P times this. So to get rid of this and get the P by itself, I'm going to divide by 1 plus RT. And if I do it to that side, I must do it to this side. So here, the 1 plus RT's cancel out, and I get then P equals A over 1 plus RT. And that's a formula that you'll be using from time to time in Chapter 3. In this next example, we're going to give you some background on inequalities, which will then get into solving some inequality expressions or equations. And first of all, these are inequality signs. The point of the inequality sign is always toward the less side, while the wide open end of it is toward the greater side. So we would describe this as saying 3 is less than 5. Negative 6 is less than negative 2. 0 is greater than negative 12. Now, to really understand this, you need what is called a number line. And on this number line, you might recall that in the middle is 0, and then anything to the right of 0 is a positive number. Anything to the left of 0 is a negative number. So anything on the number line that is to the left of something is less than. Anything to the right of something is greater than. So as we see this, here's where our 3 is, and there's where our 5 is. So 3 is to the left of 5. Therefore, 3 is less than 5. Now, if you said 5 first, 5 is greater than 3. And then over here, we'd have a negative 2 and a negative 6. And negative 6 is to the left of a negative 2. And then way out here, I guess I can extend that a little bit and say there's where negative 12 is. And we see 0 is to the right of negative 12. So 0 is greater than negative 12. One of the areas I might mention is that students, when they see the number 12 and a negative 12, you might think, well, these numbers are the same because it's 12. But remember, negative 12 is over here, positive 12 is over there. So they're completely different numbers. So that negative sign really makes a difference. And, you know, you'll say, oh, I meant to say negative. Well, negative's over here. Positive 12's over there. So in math, you have to be very, very careful with the signs. Now, in our textbook, they give us lots of other stuff that I'll go over here as sort of background, just to put you in the know of things. There's your number line. Now, if I want to say, let's say x is greater than 12. Well, on a number line, you'd look for where 12 is. That's the number you'd be interested in. And how do I indicate that x is greater than 12? Well, first of all, is 12 included in that set of possible answers? And the answer is no, 12 is not included. So back in high school, we sometimes would put like a circle, and then to indicate those, we darken the arrow, and it would look like that. So that would be the graph of this. But here in college, it'd be hard to put that little circle on the typewriter. So what we use for a inequality symbol where it's not included in the set, it's greater than, we use a parenthesis at the number. Now a modification of this is to say x is greater or equal to 12. For this one, instead of using a parenthesis, because now we know that 12 is included in the set, we change that to a bracket. So this is key. And then if it were x is less than 12, we'd have a parenthesis facing this way. And then less than or equal to, it would be a bracket facing this way. And I should mention that in other video presentations on our site, which is UNT_math_zone. I have given some basic information on this. Here, there's assuming you know it and just reviewing it. So if you want to get more basic information, you can go to the other site, but we'll include some of this stuff here as well. In example 5, we're asked to do some things that we introduced just a moment ago, but we're now going to put some names to things. This is set builder notation, interval notation, and to graph. Well, actually, this example is written in interval notation. We want to put it into set builder notation. And to do so, we would say that x is such that, now here our x is going to be in the middle. This is going to be a -2 there, and this is going to be a 3 there. But we now have to put our inequality symbols in there. And what does this say when it's a bracket? Well, we know it's going to be, this is going to be less than or equal to because of the bracket. And because this has a parenthesis, this is only going to be less than. So here's our interval notation. And from that, we're saying that x is sort of in the middle there. And what is x? Well, x is going to be greater or equal to -2, and x is going to be less than 3. And you'll probably need some practice on this as well. So here's our graph, which will be a number line. And the numbers we're interested in is a -2 and a 3. And what do we put on this number line? Well, to indicate that a -2 is in the set, but it's less than, we're going to put a bracket like so, and that this is less than 3, and 3 is not in the set, we're going to use a parenthesis, and then fill it in like so. So this is our set builder notation right here. And I believe in our text, all they want us to write is this part of it. And then this is our graph. And this is our interval notation. Now often, what you're going to start with is this inequality. And if you were to graph this inequality, it looks like this. And then to put this inequality that you've graphed into interval notation, notice how easy it is right from the graph that you're going to use a bracket at -2, comma, going up to 3. 3 is not included in the set because of the parenthesis. Okay, now this one is sort of in its equation. To put it in set builder notation, all we would have to do is put a bar, an x there, braces. But again, they're asking us to write this in interval notation and also to graph it. My suggestion is always do the graph first. Our number that we're interested in is a -5. The symbol of inequality is greater than or equal to. So we're going to use a bracket that's going to face to the greater part. And since it's equal, that's the bracket. And it'll start there and go on and increase to infinity. Now, how do we put that in interval notation? Well, it's going to start here. So a bracket at -5, comma. And where is it going? What's out here? Infinity. And in infinity, we always end it, we don't end it, but we indicate it with a parenthesis. So there's the set builder notation, the original equation, there's the graph, and there's interval notation. That's a little better. Okay, we've changed rooms a little bit, as you probably could tell. We're going on to example number 6 now, where we're dealing with an inequality. And all of the methods we use to solve equations are pretty much the same for inequality, except for one thing, and when we get to it, I'll show that to you. But rule 1, get rid of fractions. There are no fractions. Rule 2, get rid of grouping symbols. So we're going to do that right now. So we got rid of the parentheses by using the distributive principle, and we're now going to collect like terms. Well, there are no like terms to be collected on this side, so we'll just write it again, 4x plus 6. Here, the only like terms are these two, which result in a -2. Now, normally I wouldn't solve it this way, but I want to show you something, so I will. I'm going to move the 6x from this side to this side. And I can subtract 6x, or I could just transpose it, and I end up with a -2x. And now I want to get this 6 over to the other side. So I'm going to subtract 6. So I get a -2x is less than a -8. Now, I said at the beginning of this example that when we solve inequalities, everything is pretty much the same as equations, except this one thing, and that is if you ever have to divide by a negative, that is, divide by a negative, in order to keep an inequality true, you must reverse the direction of the inequality sign. So this will then become x, a positive x, is greater than 4. And the reason for this is, and I can show it to you, if I say 2 is less than 6, we know that's a true statement. If I multiply that 2 by 2, and I do it to both sides, I get 4 is less than 12. And that's true also. But how about if I multiply, instead of it being a positive 2, is a -2, this becomes a -4, and this becomes a -12. Now, is a -4 less than negative 12? And the answer is no, that's not true. In order for this statement to be true, when I'm multiplying or dividing by a negative, I have to reverse the direction of the inequality sign. And that's the basic rule we're going with here. Now I'm going to show you how to solve this another way, and you'll see the difference. Now, I always tell my students, try to keep your variable positive. And there's a reason for that. By keeping it positive, I don't have to divide by a negative. So watch what happens. I'm going to subtract 4x from this side. 4x from this side. This gives me a positive 2x. I'm going to add 2. Add 2, I get an 8. Now, when I divide by 2, I get x, reading it this way, is greater than 4. That's what we had the other way. But I had a negative was less than something. But if I kept it as a positive, which is what I've done here, I don't have to reverse my sign. But I have to read it this way. And you could rewrite it this way too. Most are accustomed to read it from left to right. Remember, the wide part is toward the x. So x is greater. Now, in following what we've done, how do we put this in set builder notation? Well, we put a line here. X is such. How do I graph this? Well, the number I'm interested in is 4. And this says x is greater than 4, so I'm going to use a parenthesis facing right, darken it. There's the graph. And then now interval notation would be starting with 4, and I need a parenthesis, and it's going up to positive infinity. Now, if this were equal, it's not, but if it were equal, the only difference is this would be a bracket and this would be a bracket. Okay. All right, looking at this is a double inequality, or a compound inequality, where x is in the middle, and we're asked to solve it. Well, again, similar techniques to solving an equation. We want to isolate the x. So the first thing we need to do is get rid of this 3, and I'll use this method. That is, we have to take away 3 from this, this, and this. In a sense, each part of our inequality. So this becomes a negative 6 is less than 2x. This cancels out. And this becomes is less than or equal to 6. Now we want to, again, isolate the x by dividing the numerical coefficient, which is a 2, and that's each term. So this becomes a negative 3 is less than x is less than or equal to 3. So to put this in set builder notation, we just put a line there and say x is such as that. To graph it, the numbers we're interested in is a negative 3 and a positive 3. And what sign do we put here? Well, this is less than, because x is greater than, it goes this way. Here x is less than, going this way. But it's also equal, so we're going to put a bracket there, darken the center, and that would be the graph. And then set builder notation, again, there's this one. Interval notation is just right from the graph. Parenthesis, put our -3 in there, our 3, and our bracket. Now as you do these, you're going to have lots of practice and various examples that will be given to you in your Math Zone application. And hopefully you have the skill to do it. In example 8, we have what is called an application problem. And of course there's a paragraph that gives you this information. I've pulled out the information I think is relevant. You've purchased a computer for $851.26. That was the purchase price. The shipping, and that included the shipping of $57, and it included a 5.2% state sales tax. And all of that is in this total amount here. But what they're wondering is, what is the cost of the computer all by itself without the shipping and the state tax? And that's, in a sense, our unknown. And that's when the magic X comes in. X is the cost of the computer. And how do we figure out what that is? And of course, there's where the algebra comes in. So what we want to do here is to set up an equation. Now, I've read this over a couple of times, and if you have a problem similar to this, you'll have to read it over a couple of times too, or maybe even more, or in some cases, less. So let's start off. We're going to say that X is the cost of the computer. And to that, we're going to add this tax. Well, how do I convert that to the tax of this amount? Well, I have to change this to a decimal. This is in percent form. This is in decimal form. I just take away the percent sign and move the decimal over 2 places. And that's going to be this much of X. That's the same X there. Plus my shipping, which is $57. And we said that cost the purchase price of $851.26. So again, you have to think about it a little bit, be creative. X is the cost of the computer. This is the amount of tax you're going to pay on that X amount. This was your shipping. And this was the purchase price. So we need to, again, combine like terms. Remember, there's a 1 in front of any letter that we just don't write. But we do write it here because we need to combine these. So this then becomes 1.052x. I'm combining one x and this to get that. I'm now going to subtract 57 from both sides. And I will continue this. So when I subtract 57 from both sides, I get $794.26. And now I have my total equals this. Now how do I get x all by itself? Well, that same principle of dividing both sides by the numerical coefficient of x, which is 1.052. And this is where your handy calculators come in. And I get x equals this. So this is what x is, but what is x? Well, if you recall the original question they asked, what is the cost of the computer? Well, the cost of the computer is $755. And we did it through setting up our data into an equation, solving the equation, and getting an answer. In example 9, we want to find out what will be our break-even point on the production of DVDs that we're making. Now we have determined that when we make DVDs, it's going to cost us in equipment to produce, copy these DVDs, and that cost in equipment and materials, so to speak, well, not so much the individual DVD, but setup. The equipment needed to make these DVDs is $48,000. Now, to produce one DVD, I need electricity, I need to pay somebody, I need the actual DVD itself. So to cost, once we have the equipment to make it, to produce a DVD is $12.40. Now I'm looking, and I have some type of graph here, where this is my 48,000, that to produce these, as I increase the number of DVDs down here, that my costs are going to increase because I'm making them, and then I'm going to sell them. And as I sell them, I figured out I'm going to sell them at a reasonable price of $17.40 for each DVD. So I'm starting at here with no sales at all, and I'm going to have a graph that looks like that. Now at this point right here, these two lines of my graph intersect, and this is called the break-even point right there, where these two graphs intersect. And I want to find what would be the number of DVDs that I have to sell where I break even in my manufacturing endeavor here. Now, what I've done is I've set this up in what we call function notation, that you may or may not be familiar from an earlier course. This is called a cost function, that the cost of producing this many cassettes is what each cassette would cost to produce. This is their number. And this is the startup fee. And this is the revenue function, in which the revenue, the money that I bring in from selling this many cassettes, or in this case, DVDs. And I'm going to sell them at this price. So I'm looking for when these are going to come equal. That is, they're going to intersect. So the way we solve this type of problem is that we write it as an equation. We say that 17.40x equals 12.40x plus 48,000. There's our equation. And I should put this dot down here. There you go. So what do? Well, we solve for x. We're going to subtract this from both sides. And this leaves me with 5x over here, because that subtracts nicely from that. And then I divide both sides by 5. That gives me my x all by itself. And I find I get 9,600 as a value for x. Now, what does that mean? Well, it means that I would sell 9,600 DVDs at that spot right there. That is my break-even spot. So if I sell one more than that, that's going to bring me a little bit higher than my cost, and I've made a profit. Wow. And that's how example 9 is done. And you'll have some to figure out as well. And I believe this concludes our lesson for our first lesson, 1.1. Looking carefully at the book, I see there's one more example, number 10, where they give you some background material on the CPI, Consumer Price Index. And that is a kind of scientifically calculated comparison of what does it cost to live in a particular section, a country or whatever. And in 1960 it was this. And 1975 it was this. 1990 and then 2005. And you see the Consumer Price Index increases as time goes on. Well, this could be used to make comparisons. So for instance, let's say in 1960, the salary earned by someone was $13,000. Now, based on the Consumer Price Index, what salary would this be equivalent to? And to figure that out, you would set up what we call a proportion, where X would be your salary in 2005. And remember that Consumer Price Index was this. And in 1960 it was this, and Consumer Price Index was that. So we're setting up a proportion that in 1960 would be there, and this would be 2005. So all of this line would be from 1960, and then 2005, we don't know the salary, but we know the Consumer Price Index. So a technique that we use in algebra to solve something like this is to, what we say is we cross multiply. we're going to multiply x times this and get that. And then we cross multiply this way, this times this, and we get that. And then using our technique of solving, we're going to divide both sides by 29.6. These cancel out, and we're left with x. We do our division on our calculator, and we get this. Now remember, we're asked, what is the salary in 2005? Well, put a dollar sign there, and that would be our expected salary. I remember when I started to teach back in 1958, my starting salary was like $3,310 for the whole year back in 1958. And by the time I left teaching, why, you know, I was like many more. I think my final salary was $63,000 in 2002. And I'm assuming that sort of kept pace with what I was doing. So you get an idea of how, if you have data and you can make a comparison, that would set up a proportion, and this would be the method to solve it. Okay, this finishes topic 1.1.